So today we actually have some sort of mini announcement or some news that we want to share with all of you guys. And that's that we would like to thank LIFO and the Wizards of Ord for sponsoring Technically Bitcoin. You know, we're super happy about that. Obviously, working with LIFO is a great contributor to the Bitcoin and Ordinals ecosystem, and so we're just super excited to be working with him, and super excited that he is supporting Technical Bitcoin so that we can make it better, so that we can make more edits, we can make it hopefully more attractive and more educational for everybody. So would love to thank LIFO again, and Tyler, please feel free to chime in here as well.
Yeah, no, huge shout out to LIFO. He's been in Ordinals since the beginning. I think Wizards of Ord, his other collections, they really embody the Bitcoin ethos, which is my favorite part of Ordinals. I say it over and over again, and it remains true. So we're really grateful to LIFO, the entire Wizards of Ord community, for that generous donation to help us pay our editor to keep producing these things. It really means a lot to see that validation come from the community. So thank you again to Wizards of Ord, and we're really excited to continue producing these for you all.
Here we go. What's up, everybody? What's up, Tyler? How's it going today?
It's good. I'm excited. I think Merkle Trees are super cool. They're just one of the neatest things that computer scientists have figured out. I hear they're a hot topic today in Bitcoin, so I figured we should teach the degens a bit about what these things actually are.
Yeah, we have to do it. As you guys know, on Technically Bitcoin, we're trying to demystify some of these things that you have probably heard about, but myself included, I actually have never really looked into it in depth. And so today we're going to talk about Merkle Trees because they're very important, kind of a foundational pillar of Bitcoin, right? In general, or blockchains even, we can say. But obviously we are focused on Bitcoin, so let's talk about Bitcoin. And, you're going to learn that there is a lot of connection with a lot of these different L2s and CAD VM and stuff that is kind of being built as we speak. And so that's why we believe it's important for you to kind of at least grasp the basics of what these things are and what they represent, what is the logic behind it. So Tyler, as always, please walk us through it. Let's start with some sort of overview and then let's go a little bit deeper.
Perfect. Yeah. So to give you all a sense of what's going to happen today, we'll talk a bit about what Merkle Trees are, kind of just at a high level. And then we're going to do a quick review of hashing. We talked about it a bit in the mining episode, but it's really important in Merkle Trees. And then we'll get into how Merkle Trees actually work and why Merkle Trees and OpCat, how are these related? Why do we keep talking about them in Cat VM? And I hope by the end of it, you'll get a sense of why these Bitcoin L2s are so excited about the potential of OpCat and Merkle Trees.
Amazing. Let's go. So the overview. Who invented this?
All right. So here we see the lovely gentleman, Ralph Merkle, who is actually one of the godfathers of modern day computer science and networking as we know it. So go check out his Wikipedia. He looks like a total badass in his Wikipedia photo here. And that's because he is a total badass. He created basically the foundation of public key cryptography, which, as you all know, we use in Bitcoin to keep your Bitcoin secure. He also invented hash functions, which are what we use to mine. So he was one of the first people who created, an early version of a hash function. And then finally, based on those hash functions, he actually created the thing we're going to talk about today, which are Merkle trees. And so I put him up there just because, he's a cool guy to go read about. He really had a big role to play in really your computer being able to work the way it does today. Not even just Bitcoin, but all of that. So pretty cool dude. So wanted to give him a shout out before we dive into one of his namesakes, the Merkle tree.
Yeah, absolutely. So yeah, what is this all about? I think the first phase of this overview, maybe we don't have to go into so much depth, but what does this even mean? Like Merkle tree, obviously it resembles a tree for a reason. So what does this even mean, and what does it do?
Yeah, so Merkle trees are a way to efficiently store and verify data. So I'd like us to just keep an open mind here and say we want to store these 4 transaction IDs here. And
Hmm.
we want a way to know that they're all, somehow there. When there's only 4, it's really easy. You're like, okay, great. I say almost think of it like a film strip that you would be running over, and so here's the data we care about. We're gonna put this all in a computer's memory somewhere, and you can think of it like scenes in a film or something. As you pull the strip by, you see the scenes go by, more data comes by, and so that's great. But it turns out if we add a little bit more, we get a really cool property out of it. And so if we basically create these branches and go up to the root, we end up creating what's called a Merkle tree.
Hmm.
And so when we create a Merkle tree, it'll look something like this. It's, these true transactions roll up into this branch 0. These 2 transactions roll up into branch 1. And then branch 0 and branch 1 somehow combine to create this root. And they do that through 2 things. They do it through concatenation and hash functions. And so that may give you a little spoiler as to why we're so excited about potentially adding opcat back to Bitcoin. Now, if we do this, we get 2 really cool properties back. So if we add these branches, if we calculate these essentially from the data down here, we get 2 really cool properties. One is that this root, just this root, commits to all of these transaction IDs. So if you take all these transaction IDs and you store them in a Merkle tree, if you then went and changed transaction ID 2, even like 1 character, the entire root of the Merkle tree that would be created with the slightly malleated transaction ID 2 is totally different.
Hmm.
And so that's really important. That's why we say the root of a Merkle tree commits to all of the data inside of it. And then the second thing it lets us do is it lets us efficiently check if certain pieces of data are in there. And so this is where why I have transaction IDs here to give you a real life example within Bitcoin. Every Bitcoin block header has a Merkle root in it. So every time a block is created, what actually happens is in the Bitcoin node software, it is storing all of the transaction IDs in a block inside one of these Merkle trees. Why would it do that, you might ask? Well, it turns out that if you just want to confirm that your transaction yawn was included in the latest block, in order to do that, and in order to make sure the blockchain committed to the right block and everything, the naive way to do it would be to say, give me all of the transactions in the block so I can verify that it all rolls up to this thing that you said. But it turns out with Merkle trees we can do a lot better. We can ask for a lot fewer pieces of data and get confirmation that our transaction ID was included. And so if you ever hear the term like a light node, that's actually what a light node is doing. It's just verifying the block headers, and then it's just going and checking and saying, okay, I'm going to go fetch the transactions I care about, but I don't care about the other transactions. I just care that the ones in my wallet work. So, for instance, an Electrum server allows you to do this.
That's super cool. I think maybe, do you have that example of, like how much data you need if you want to verify all the transactions without a Merkle tree and with the Merkle tree? Because I think maybe this is the best time to actually show it instead of
Yeah.
waiting till the end, because it really kind of proves the point of the efficiency, right? And obviously we can kind of go back and look at the logic and how we can kind of like do this or how the program is doing it. But if you can maybe zoom in onto that data point, I think this is going to blow people's minds.
All right. So yeah, this is what Jan is talking about. So you'll see this in the say, while Merkle roots take a little more effort to construct, right? We're adding things on to just the raw transactions. They save a ton on bandwidth when it comes to verification later. So this is an example from an actual Bitcoin block. And if this is a Bitcoin block and it has 2,351 transactions in it, and if you want to verify that your transaction exists in the block without a Merkle tree, you would have to download 75 kilobytes of data to check that your transaction is there. Now, if we have a Merkle root and we've stored this in a Merkle tree, we only have to ask for 384 bytes of data. So when we say, what we say is Merkle trees give us exponentially better verification by storing data in this particular way. And so hopefully that gives you some intuition around why this is so useful in networking applications. And just, Bitcoin is not the only blockchain to use this. This has been around networking theory and how computers communicate since Ralph came up with it, way back in the 70s.
Just one more clarification. So basically they mention here without a Merkle root. So basically for people to understand, obviously we have the Merkle tree is basically, the whole thing, right? Like that's kind of like the idea that we're using, or this like, I don't even know how to call it, but it's this construct that we're using, right? And then if you have the Merkle root, which is the basically the core of the tree, right? The beginning of the tree, and you want to verify all the transactions, you need much less data than if you don't have it. If you would just basically have to, as you said, download all the data, all the transactions, and manually check, okay, is this in? Is that not in, right? So I just want to make sure that like this Merkle tree, Merkle root, and how does it relate to each other is clear for people so that they don't get confused with this terminology.
Totally. And we'll go through a few more examples so we keep talking about the root being that top thing of the top piece of the tree, and then at the bottom what we call are the leaves, and then there are branches that go down to get us to the leaves. So I think that gives us a good intuition of what these things are, and at least one
why they're useful, right? I think this is kind of just to the point that this is super useful for even companies like Xverse. We talked about it, right? Because you want to verify, okay, did this transaction got confirmed in this block, right? Like, should I display your ordinal in your wallet, right? And I guess that's kind of like what we're taking advantage of, because if you had to download every single transaction or all this data in each block just to verify one transaction, it's just going to become like very inefficient, probably not good for the servers, not good for the speed of like loading everything, right? But if we suddenly, instead of like 75,000 bytes, we only need 300 bytes, obviously it becomes like a lot more efficient. So yeah, like this is basically why these things are so important. And obviously, I guess every single builder, every single company that is building something in Bitcoin is using these things and is taking advantage of these things.
Yeah, absolutely.
Yeah,
okay.
So Tyler, so we talked about obviously kind of Merkle trees, how they came to be and why they're so important. And in that you mentioned that you're hashing certain information, certain data about these transactions together to basically, again, like make stuff again more efficient, or it's related to cryptography and all of these different things. So let's just refresh our memory of what hashing actually is, what it means, because we talked about it briefly in the mining episode, for which it's also very important for the miners. The hashing is very, very, or it's basically vital, right? Like without that you cannot really do anything. But let's refresh our memory here. So what is hashing? And maybe let's run through these examples because I think they're pretty cool.
Yeah. So for our purposes today, we're going to be talking about a hash function. So just over here, when you see this thing, SHA 256, it's called SHA 256 is how we say it. in computer science speak. But and SHA-256 is a hash function. And what hash functions do is very simple. They take data of any size and they produce a unique and fixed length output. So in the case of SHA-256, and this is the hash function that's used in Bitcoin mining, the output is 256 bits long, or 32 bytes long. So that's why it's called SHA-256. It takes an input of any size and it gives us a 256-bit output. And so that's what you see below. This is what you see in our examples. Now, what is unique about this, and the other property that we really care about, is that if you are given a hash, if I give you this 5C, 5dB, all the way, blah, 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 487, Jan, and I don't tell you anything else, you have, except this is the SHA-256 hash of something, you have no way of figuring out what that input was. So without, essentially we say no knowledge is leaked from the pre-image that Jan is of the hash to the post image, which is this long 32-byte number. And like as an example, like what you can really see here is that we have both, you know, Jan with a capital J and Jan with a lowercase j, and you see completely different numbers. It's not like they're off by 2 or something. They're off by one of the largest factors they can be off by. And so that's a really important part of hashing. The second thing that's really important is that it will always generate the same output for the same input. So Jan, I put this in my SHA-256 hash. I tell you, Jan, you go home and put Jan in your SHA-256 hash function. It will always give us the same output. So this is a good way for us to verify data. And this is actually why the hash locks that we talked about in the previous episode work, is we know that for a fixed input, they always give the same output. And then the third cool thing is that they can take data of any input size. So originally here, I actually had the entire abstract to the Bitcoin white paper, but it took up too much space. So I cut it down to the first sentence. But you can go take the entire Bitcoin white paper if you want. Actually, just Google online SHA-256 hasher. You can drop the PDF in there and it will give you a SHA-256 hash of that PDF. And so it's really cool that you can give it, you know, data of basically unlimited size, and it will spit out this output that's only 256 bits long. And you know that for each piece of data that goes in, it is like almost impossible to get two pieces of data that generate the same output, right? The probability is literally 1 over 2 to the 256, which is just like an unfathomable number, low probability. We as humans don't even know how to conceive of how unlikely that is to happen. And so what that means is that, you know, let's say I wanted, you know, Jan, you've done something with a hash function and you're like, it's really important that the input be Jan and I don't want anyone to know it. Or actually, here's the best example. We use this for our passwords. So Xverse, you offer me a password. When you store my password, you don't store the password itself. What you store is the hash of my password. And when you want to check, when I'm logging in, I put in my password. You don't go and say, let me compare it to the database. On my computer, you take the hash of it. And then that's what gets sent to the Xverse server. And the Xverse server says, okay, these hashes match up. Tyler must have given me the right password because there's no way any other password would create this hash. All right. So we're just going to do, we already talked about this a bit in the beginning, but we're going to talk about how Merkle trees are actually formed, and then we'll get into the cool properties of them. So this will be a very quick and simple example. Merkle trees are very easy. They are formed through two functions, concatenating and hashing. And again, this is why we are so excited to potentially get cat added back into Bitcoin script so that we can do some things with Merkle trees, in with actual Bitcoin. So the example here, very simple. I've put a transaction down here just so we can imagine that there is some data. So imagine, this is A, this is transaction ID for A. Imagine that there's another one for B, C, D here. So these are, again, what we call the leaf nodes. So these are the leaves of the tree, this bottom layer. And what we're going to do to start building the Merkle tree, because we have all this data, it's very simple. We take the first two leaf nodes, A and B, and we're going to concatenate them together. So we'll write that in here. Actually, I'm going to write it a bit bigger. So we're going to take A and then these two bars. That just means concatenate in computer science. So if you ever see that, it's what people are meaning. We're going to concatenate A and B together, and then we're going to take the hash of them. And in the case of Bitcoin, we'll take the SHA-256 hash. And let's say that, that's going to produce an output, just like we saw in the previous section. It's going to be 256 bits. Let's just call that output X. And so now A and B have rolled up into this output X here. Then we just go on to C and D, and we say, okay, great. C and D need to roll up into another output. What are we going to do? We just take the hash of C concatenated with D, and let's say that this equals something called Y. Great. Now we have X and Y. These are just two numbers, 256-bit numbers. And now we want to get to the root. So we're just going to do this operation one more time. We're going to take the hash of X and Y, and that is going to equal what we'll call the root of the Merkle tree. So now up here, this is the Merkle root. And then what we like to say is that these little side things, if we kind of draw a line around here, this is a branch, right? So this is a branch of the tree. It stems out from the root and goes all the way down to the leaves. So that's the terminology that we use around Merkle trees. So any questions around that, Jan?
No, I think it's pretty cool. I think one thing that maybe you should touch on here is because, we have the Merkle trees, and as we discussed, this is related to the Bitcoin nodes, right? Like this is kind of like how you construct the Merkle tree inside of the nodes inside of each block, right? Because you have a Merkle tree for every block. That's also something for people to understand. And so on one hand, it's basically putting together the data of each block in Bitcoin into this construct of Merkle trees. But then on the other hand, you actually mentioned very interesting stuff is if we get opcat back into the Bitcoin script, then we can do these similar things and we can actually move Bitcoin around and we can program Bitcoin transactions, right? And do more complicated and cool stuff with it. So can you maybe like draw a line there or maybe explain to people how these things are different? Because many people maybe hear, okay, we don't have opcat in Bitcoin now, but you're telling me that you can actually put things together to create a Merkle tree today. So like, I just want to make sure that people are not confused by these two things. Yeah.
So I think you bring up a really good point, Jan. I keep talking about Merkle trees, how blocks use Merkle trees, all this stuff. And you're like, well, why do we need opcat? You're telling me that Bitcoin uses Merkle trees already. Xverse can do this Merkle tree verification already. What do we need opcat for? Well, if we think of the entire Bitcoin protocol as, this is giant space here. There's a ton of code that goes into all of this. Some of the code tells us how we can spend and basically like restrict the spending of Bitcoin. And that's what we call Bitcoin script. So opcat is an operation within Bitcoin script that we don't have right now. And so that's a piece of the Bitcoin protocol, but there's a ton of other code in this code base. So there's a whole nother section of code over here, and this is basically our networking code. So when you run a node and it's like, how do I know what to connect to? This is a node, this is a node, this is a node, this is a node. Like, there's a program that tells Bitcoin nodes how to talk to each other. There's another program that tells Bitcoin nodes how to like verify that blocks are valid. And so, there's all of this other, networking, like this is the networking part of the protocol. That part of the code has Merkle tree verification. It knows how to create Merkle trees and do all this stuff. That is very different than saying within Bitcoin script, you can encumber your Bitcoin. You can lock your Bitcoin to something that requires a Merkle tree verification, or you can store a Merkle tree in Bitcoin script, or you can verify a Merkle tree in Bitcoin script. We can do it in the protocoling networking side of Bitcoin because it's already baked in. Like, it knows how to do this. We cannot do it in script, and having it in script is the key unlock for something like CatVM, where we're actually going to want to use Merkle trees and verify them within Bitcoin script to make this like nice bridge over to, a better way to use Bitcoin.
Got it. So long story short, you actually cannot do Merkle trees today in the Bitcoin script, to basically, as we discussed, like restrict the flow of Bitcoin, right? Because
Right.
we don't have opcat, we don't have the concatenate operation in the Bitcoin
Exactly.
script. So that's kind of like the distinction that I wanted to make also for people, to understand when you say like, okay, we don't have opcat in Bitcoin, you're referring to the script, not to how basically, the transactions and IDs and stuff is stored and constructed in Bitcoin, the network, the nodes and stuff like that. Like, I think we just need to make that distinction here.
Yeah, I think that's a really great point.
Awesome. Yeah, I just wanted to bring that up. Other than that, I actually don't have any other question. I think we should just go and maybe finish up with an example of how you actually kind of use the logic of Merkle trees to get to the information that you want. Basically, you explain, okay, like you have these transactions, these leaves and branches and the root, and obviously you always can like go up to like, I guess, infinite number of leaves, right? You can always like double the amount of leaves. And so now if you can bring out an example like, okay, I have this tree and I want to verify this specific transaction or this specific hash, like how do you do that? Like, how do you kind of make it efficient in terms of the data needed?
All right, so this is the big unlock. This is what we get excited for when we talk about Merkle trees, is being able to do this verification. So when data is stored in a Merkle tree, what I say is you need exponentially less data to prove that it is there, that it has been committed to by the root of the Merkle tree. So the question I'll pose to you, Jan, and we'll play like a little game here, is how can we verify that C is included in the Merkle root? And I'm gonna add a little wrinkle in there, and it's like, not just how can we verify it, because a very simple way to say that C is in this Merkle root, the Merkle root commits to C, would be by me giving you all of the data, right? I could give you A, B, C, D, E, F, G, H, and you could do the concatenating and hashing, and you could get the root itself, which is fine. But it turns out there's a better way. And so, pop quiz, which of these pieces of data would you like to have if I told you here is your transaction C, here is the Merkle root? What other pieces of data do you need to check that C is in this Merkle root?
Got it. So I would like to just say, maybe for people to understand what is actually happening here, right? Like, as we mentioned at the beginning, the Merkle root is basically like a hash, right? And so, all that information, well, I don't know how to say it, but like, I kind of want to say the fact what you mentioned is that we're basically verifying if it's there, because if it's not there, then the Merkle root is going to be, it's not going to match, right? It's going to be
Right,
completely different. So
right,
if C is missing from this, or if it's different, let's say if
right,
C is a little bit different transaction, then the Merkle root that I have been given, that I have right now, is not going to match with the one that I'm going to create from that information, right?
exactly.
From that new information. So I think this is just something important to understand for people. Just kind of going back to what we discussed at the beginning, and now going to the efficiency, right? So if I look at this tree, and then I'm only interested in, from my perspective, into the left side, right? Because I'm verifying where the C is. So I need to
Hmm.
figure out the easiest way to get to that. Because the right side, like, I just need B, right? Because basically B is representation of all the branches and all the leaves under it, right? And so
Right,
if I have B, I have the entire part of the right side. And
yeah,
that's basically, let's say, half of the root, right? The second half
right,
of the root is A. And now, okay, so I need to get to verify the C. So in that case, I need to create that A, right? I need to be able to
hmm,
get that A from you, or I need to be able to get it. And so in that case, I need to create 0 and 1. So, well, not create, but you need to give me 0 and 1. So to give me 0, you just give me 0. And
hmm,
to get 1, you give me D, because C and D equals 1 or creates 1, right? So you basically get me these pieces of information, which means that I am able to get A and B, the root. And now I just need to verify, okay, are they the same or not, right?
yeah. So that's right. And let's kind of like walk
Yeah,
through
let's
this
walk back.
example here. So Jan asked me for three pieces of data. He asked me for B, he asked me for 0, and he asked me for D. And like let's talk about the logic behind that. I think Jan walked us through it, and let's go back through it again. Jan wants to check that this Merkle root commits to C, right? And that C wasn't changed. So if
When,
he
when,
was
when you say
given,
commits, maybe Tyler here, what do we mean by when you say it commits to? When you say it commits
yeah,
to, it basically means that it includes, or what does that
yeah,
mean?
I think includes is a good way to think about it. And why I say commits to it is that if you were given all the pieces of data A, B, C, D, E, F, G, H, and you did the concatenating and hashing to get to a root, you'd get to a certain root. If let's say I tried to cheat and C was a transaction sending Bitcoin from you to Udi, and now I go in and I like somehow try and replace that, and it's a new transaction and it sends Bitcoin from you to me.
Yeah.
Now, if you take this same data, this D, this 0, and this B, and you reconstruct the Merkle root, you're going to find that it is a different root than the one like you thought it should be, right? So when we say commits to it, essentially what we mean is that if any of this data in the leaf nodes changes at all, the entire root is going to change.
Yeah.
Um, and so what we want to check again is that C, this root commits to the data in C. And how we can do that is Jan said, okay, first give me D. Well, at first he said B, but I'm going to go through it a little backwards, and I think
Yeah,
it'll
yeah,
help
please.
clear up the logic, right? So he said, "Give me data D," and then he said, "Okay, what I'm going to do is I'm going to take C and D, and I'm going to concatenate them and hash them together, and now I have one, right? I've constructed one from C and D." And okay, well, now I need to get this information in A. I need to get to A because A and B combine to make the root. What do I need? Well, I have one, but I don't have zero. So, Tyler, please give me zero. And now, again, I just take the data in zero and one and I concatenate and hash them. And now I've constructed A. And then I said, okay, Tyler, I need you to give me the data in B because I don't know anything about E, F, G, and H. I don't know about these transactions. But if you give me B, then I can take A and B and concatenate them and hash them. And what that should equal is the Merkle root that you gave me, right? So you gave me a Merkle root and C, and I said, now give me all this other data, and that other data was D0 and B. And if D0 and B, and I do this operation, turns out to be the same Merkle root you gave me, then I know that C is in this Merkle root, right? You didn't cheat. You didn't do anything nefarious. But what I didn't have to ask about is what are these actual transactions EFGH? I actually didn't need to know anything about that. I just asked for B. And so the really cool property here is that, remember, you started with C and the root, and you asked for 3 pieces of information. You asked for C, you asked for 0, or sorry, you asked for D, you asked for 0, and then you asked for B. So this is piece information 1, 2, and 3. That's very different than going down here, and if you had asked for every piece of information, you would have had to ask for 7 pieces of information. You needed to say, give me A, B, D, E, F, G, H, right? That's like a little better in the case of 8, but you can imagine that when we keep doubling and doubling this gets exponentially better. And so what we say is that the number of pieces of information you have to ask for is the depth of the Merkle tree. So for each layer below the root, you can see there's here layer 1, here's layer 2, here's layer 3. That's how many pieces of information you need to ask for to verify, that any given transaction is in the Merkle tree. And so if we did this again, let's say this is now, instead of 8, this is now a 16, a 16 pieces of information rolling up. Well, if you ask for every piece of information, you would need 16 pieces of information, or 15. But with Merkle tree verification, you only have to ask for 4. And if we do it again, you're going to get 32 and 5. And you can see that this very quickly gets us to the point that we talked about in the very beginning, where we said you either have to ask for, 73 kilobytes of data or 380 some bytes.
Yeah, I think that's pretty clear. I don't have any questions here, Tyler. To me, it's easy peasy now. I guess hopefully everybody understands how you do this Merkle tree verification and why is it so much more efficient to do it with Merkle trees, or verifying stuff with Merkle trees and hashing, instead of just like downloading raw data and having all the data, which always you can do, but that doesn't scale.
Yeah, exactly. So, all right. So the last thing I wanted to talk a bit about, for those of you that read the children's book, you'll notice that all throughout the children's book we talk about, there are images of Merkle trees. So now, if you go back and read it again, when Rindell goes into the Merkle tree forest, you'll see the trees are shaped that way. If you look at our CatVM bridge here, what you'll notice is it's actually supported by a Merkle tree, right? Here's the root, and there's a cat here. There's a cat basically at each branch you would need to verify things in this tree. And so if we have the ability to do this Merkle tree verification in script, it creates a really cool way for us to arbitrate programs. So, like, to verify that programs were run correctly. And when I say programs, it could be as simple as let's add 12 to itself 3 times. It could be as complex as Jan is trying to cheat and withdraw Bitcoin from CatVM that I don't have. But it turns out with Merkle trees and Merkle tree verifications, we can essentially both commit to the programs that we thought were run. We put all our data in Merkle trees, and then we run down until we get to these leafs and we say, here's the leaf we disagree on, or here's the step that we disagree on. And then we can arbitrate that step on chain. So it might be helpful if we do an example. I don't know, Jan, do you want to run through an example?
We can definitely do an example. Yeah.
All right, so I'm going to take us back to our original Merkle tree we talked about in the very beginning with our boy Ralph up here. And now we're going to talk about what I mean by verifying a program within a Merkle tree. So the program we're going to talk about right now is adding 12 to itself 4 times. So instead of committing to these transaction IDs that we see here, I'm gonna make 2 additional rows here, and we're gonna have Tyler's program and Jan's program. And what we're gonna store in this Merkle tree is basically our steps along the program. So my program, Tyler, I start with 12. That's my first piece of data. And then I'm going to do an operation. The operation is addition. And I'm going to say the next piece of data is not 12. That's definitely not what it is. It's continued trend of me failing at math on this show. 24. And then I'm going to add 12 again. And I'm going to say that this, I say in my program, this is equal to 37. And then I'm going to add 12 one more time. And I'm going to say that's equal to 48. And Jan, you're going to have your own program, and you're going to say, though, that it actually works out correctly. So 12, 24, 36, and 48. Now, each of us will have a Merkle tree, right, committing to these pieces of data. But with what we learned about hash functions, our roots are going to be totally different, right? Because there's a piece of data here in, under this third leaf that is different for the 2 of us. So what we'll find is that, okay, is your root the same as my root? No, because all of the data is not the same. But what we will find is we'll go and say, okay, let's look at branch 0. Now, if we look at branch 0 here, we're going to say, yeah, actually, we agree. Like, branch 0, we agree on, right? 12 plus 12 is 24. We seem to have agreed on this. Great. Branch 1, on the other hand, this is not going to be the same for both of us, just like the root wasn't the same. Again, because there's different data down here. And so then we'll go and we'll say, all right, did we disagree on step 4 here? No, it actually looks like we think step 4 is the same thing. But somewhere along the way, we seem to have disagreed. We think something is different here. And maybe to make this just even more clear, I'm gonna make this 49. And so we're gonna go and we're gonna say, okay, well, where is the first place we disagreed? We're gonna say, well, the first place we disagreed is down here at step 3. I said it's 37, and you said it's 36. And then we're going to say, well, the last place we agreed was right before this, when both these things were equal to 24. And so now what we're going to do, and this is like the really mind-blowing cool part, is we're going to actually execute this step of the program on Bitcoin. So we're going to say, okay, we're going to have a Bitcoin script. It is going to take 24. It is going to call the add function, and it's going to add 12. And that's going to equal something. And that program is going to say, well, this equals 36. And when that happens, Jan, you will essentially win this battle amongst the Merkle trees, and you will get the Bitcoin or be able to withdraw your tokens or have proved that I tried to cheat. Here, this is obviously a very simple example of a program that adds 12 to itself 3 additional times, but it's the exact same logic that applies to saying, in CatVM, we'll have an optimistic withdrawal game, and you and I will have to fight over whether you think my withdrawal of your tokens is valid or not. And we'll both say, well, this is what I think happened on CatVM, and this is what you think happened on CatVM. And instead of having to go through every single step along that program, we get to use this property of Merkle Trees to quickly figure out that single place where we disagree and execute that one operation to figure out who's actually right.
Makes sense. I think it does make sense. In that case, the only thing that I would say the 49 would be your end of the program, right? It's basically my program would still be like 48 would be correct, and I would be able to withdraw.
Right.
Because if my was 49 at the end, then it would be incorrect also, right? And that's basically, I don't know if that means that we're both wrong.
Yeah, exactly. Like we're both wrong, and so let's say you do this and you try and make a withdrawal and yours is wrong. I challenge you to show it's wrong. What happens is it's not that you win, like you don't get to keep it, or I don't get to keep it if I challenged you to show it's wrong. It goes back into the vault, basically. And now I can go try and withdraw it, but it turns out I'm wrong, and Udi comes along and challenges me. And if I lose the challenge, it goes back into the vault, and Udi can now try and withdraw it. But winning doesn't mean you get it. It just means the person who is trying to take it does not get it.
Yeah. No, makes sense. Yeah, I think this is pretty cool. And so this is an example of what we're going to be able to do. As you said, we're going to be able to bring this verification on chain, basically, because that's something that is missing. That's the missing part, missing piece of Bitcoin right now, because we don't have opcat or concatenate function in the script, which means we cannot do this on chain. And so
exactly,
it cannot be like 100% verified. In a sense, you would always have to trust somebody for the verification.
Exactly. And so once we get opcat back into Bitcoin, we're able to use this very efficient method of finding places we disagree and figuring out who is right or not. And we do that by storing the programs essentially in these Merkle trees.
Yeah. Makes sense. I mean, I don't have any other question. I think this is pretty clear. I think we should wrap it up here, because I think, it's, I think it's a simple concept. It's not anything crazy, especially if we don't go under the hood, if we're just kind of staying here on the surface and kind of explaining how these things work so that people can wrap their head around it. I think in that case, it's pretty simple. Obviously, I don't want to take anything away from Ralph, because this is probably much more difficult, under the hood, how these things are actually put together. But yeah, I think it's clear. I think it's clear how it works, why we need it, for efficiency. I don't know if you have anything else to add, Tyler, but to me, this covers Merkle trees and the potential of them pretty well.
It's pretty straightforward, right? I think we learned that Merkle trees allow us to store and efficiently verify large amounts of data. As we saw, all Bitcoin blocks are actually stored in Merkle trees, all the transactions. Merkle trees are actually pretty simple. They just need two functions. You have data and you hash it and concatenate it together until you get to that Merkle root. And that Merkle root is special because it commits to all the data in the Merkle tree. So if any piece of data in the Merkle tree changes, you get an entire new root. And then finally, at the very end, I think we gave a little toy example of what opcat will let us do, and it lets us verify Merkle trees in Bitcoin script. And that's how we can build these optimistic withdrawal games that actually power the cat VM bridges. So really today, Jan, like, I think it's very impressive. You learned how cat VM works. Like, this is it. This is the big breakthrough of cat VM, is if we get opcat, we can have Merkle trees in script, and then we can put our programs in these Merkle trees and play these optimistic withdrawal games to figure out who's right or not.
Awesome. Thanks, guys. We're going to see you in the next episode of Technically Bitcoin. As always, follow us on Twitter, X, and also make sure that you send us any kind of suggestions. If you have any kind of questions regarding Merkle trees or cat VM or even anything else that we have discussed in the past or something that you want us to discuss in the future, let us know, and we're going to see you in the next one. Peace out.
Bye, guys.